made my presentation easier, as he discussed mostly about the data compression and feature extraction at the edge. I'm gonna go in the same path, but so the work that we've done, it's on bridges and structures in general. As Eduardo was mentioning, structures are always prone to threats like wind and earthquake, and they need to be monitored continuously to be sure about the integrity of them. However, the main problem is that for the complex systems, larger scale systems, we need a very dense and scalable monitoring system in general. One of the problems is, again, as Eduardo was mentioning, is high volume of data. So zooming into the edge side, which sensors are read and then sent to the cloud wire or wireless, we can just send them without any compression at the edge, and then we have high traffic rate and we have a lot of data at the cloud to work on. And we need to have a power grid based system, because in general Wi-Fi based systems that transmits a lot of data needs they are power hungry. But however, we can do data compression at the edge, or also do anomaly detection at the edge, which we consider as stating the structure's status as safe or dangerous to be used. This is implementing these ideas is not that intuitive, let's say, and we have some challenges, which are limited memory for the tiny devices at the edge, and usually the signal processing approaches are have high latency, and they are power hungry also for the MCUs. So in our work, we work on another compression system, which is called system identification model, to compress data up to with a compression factor of 50. So far in the literature, this algorithm has been implemented on a single core device with a sequential way. We, on the other hand, focused on parallelizing this work, and we implemented it on a multi-core processor, which is called GAP9, that I'm gonna introduce you. What is it? And then finally, we profiled the energy and memory footprints versus the single core sequential implementation. Therefore, the outline of my talk, first I'm gonna tell you what is system identification, how it works, what are the sequential part, and how it can be parallelizable, which I can anticipate is QR decomposition, and how we can parallelize the QR decomposition of this algorithm. Then I'm gonna give a talk a bit, discuss a bit what is GAP9 and what is RISC-V. And then I'm gonna show you some results and conclude my talk. Okay, so what is system identification? System identification is an algorithm to model the structure, or a given structure, with the signals that we see from the structure itself, in the form of a casual linear time invariant filter, in which the coefficients of this filter, or frequency responses of this filter, can be used to have a smooth spectral profile of the structure. In our approach, we use the autoregressive models, output-only autoregressive models, to extract these modal parameters or filter tabs of the filter. Maybe I can use this. Which are the gamma and theta in these equations, to estimate, to have an estimate of the PSD, and compute the PSD by formula. Solving these equations with these regression equations with linear algebra, it's a bit complex for the tiny devices at the edge, and also it's memory hungry. So we want to tackle these two issues in with the new implementations of system identification model. So previously, in this cited work, the system identification model is implemented like this in a sequential way, by which I mean it takes the chunk of data, it makes the regression matrix to be decomposed into Q and R. Then the R part of the QR decomposition of each chunks are stacked together to finally estimate the beta and the sigma here, which is our gamma and theta in the previous slide. However, the problem with this implementation is that we have still high latency, which the one iteration of this decomposition of the whole system of model parameter takes around 1 minute. And this 1 minute is very power hungry. So we were thinking that, okay, instead of doing sequential decomposition of the QR, we can do a parallel version of it and see how it affects the latency and the energy consumption of this model at the edge. So this is here, I show the comparison between sequential and parallel computation of QR. There are two things to highlight here in the difference of the sequential versus parallel is that the sequential implementation, you see here that at each clock of the MCU, we can compute only one Q and one pair of Q and R, and then the data are used in sequential way, and each Q is dependent on the former one. However, in the parallel implementation, not only in this case we can parallelize the computation of the QR, but also we can fetch the data from memory in parallel way, in such a way that we can parallelize both from the data chunks fetched to the implementation and also from the QR computation. So that this will speed up the whole system in the end. Then having this parallelized version is not I mean, you cannot implement this in a single core device because when you have one core, you don't have enough computational core to do a parallelization. However, in a more advanced MCUs like GAP9, which are based on RISC-V, which is another instruction set architecture compared to the traditional ARM ST devices, we have up to 8 or 9 cores that we can assign each QR decomposition to each of these clusters, and then increase or decrease the latency. Let's say increase the make it faster. Let's say the computation. Another important aspect here is the memory that we have. We have a hierarchy. Sorry, hierarchical memory in GAP9 compared to the smaller memories at the state-of-the-art ST devices. So here is the custom board that we use to acquire and implement the system identification in parallel mode. I'm not going to delve into it much more, and we can come back to it for the sake of time. Then I'm going to show you some results. So here is the accuracy of the model with the comparison between what we have computed at MATLAB and what we have implemented in GAP9. This table is basically the ISD of all these configurations of the system that we have used. And you see the worst case scenario is this for this 41 model order that we have in the range of E-2 that I plotted here against the peaks, let's say, of the PST are completely matched for GAP9 implementation and also MATLAB implementation. So which means that our implementation is working. And also the ISD should be close to 1 for the ideal case of 2 implementations, which are, in our case, they are all infinitesimal and there are no high number near to 1. Then here is the implementation results that we did on GAP9. So first of all, I want to mention the speed up that we achieved by performing the parallelized version. We reached 64 times faster in the ARMA model compared to the sequential implementation. Ideally, it should be maximum 8, but why we have 64 is that, as I was mentioning before, we have 8 times for each QR decomposition, and we have 8 times for using 8 chunks of data at the same time. So 8 by 8 should be 64, but unfortunately we reached 63. So ideal, it's not even the best ideal case. Another reason for having this high speed up is due to the sequential nature of previous implementation, that we should unroll chunk by chunk and not having the full matrix multiplications in the QR decomposition. Then from the energy point of view, we are in the range of millijoule for the maximum case, and also for execution time, we reached up to 1.65 seconds instead of minutes. And the maximum memory that we use is 1.4 megabytes of data for our extreme cases. And you see that for AR to ARMA, we doubled, because for ARMA, we should iterate twice as what we do in AR. So I would conclude my talk here, but by showing this image that we took the raw data, we, instead of sequentially, we parallelized the QR and the system identification model, and we extracted the model parameters, which are theta, and we send them to the cloud, and we can reconstruct the power spectral density at the cloud with 64 times faster than what we have done before. For the future work, we're gonna also bring this last part that is done at the cloud to have something like what Eduardo did, to do fully anomaly detection at the edge. And thank you for your time.